Okay, last time we started the first half of chapter 8 and we talked about what are the principles of a battery, how the chemical reaction can convert chemical energy to electricity by transferring of electrons. So there are a lot of terminologies regarding a voltaic cell and also regarding the redox reaction. So last time we finished around here. I want to use this one kind of like a review, some of the topic we studied this chapter and maybe some more from previous chapters as well. So let's take a look at this practice about metal refining. Okay, metal refining. This practice is talking about two metals that are used in nickel-cadmium battery. Okay, and those two metals are obtained by or from the sulfur-containing ores such as nickel sulfide and cadmium sulfide. Okay, and the first question is, again, like I said, this practice not only review something from this chapter and something also from previous chapters, see if you can remember, because we're about to get finals. So the first question is, name 3 attributes that distinguish a metal from a non-metal. Okay, of course we're talking about metals here, but what do you think are 3 attributes that distinguish a metal from a non-metal?
Reactivity.
Reactivity, yes. I mean, to be more specific, reactivity means metals in a chemical reaction, they will tend to what? Lose electrons to become positively charged. Non-metals, they tend to gain electron to become what? Negatively charged. Remember, we have a charge table. Okay, the metals are positively charged, non-metals are negative charged. If you mean that, yes, reactivity is one of them. What else? What's the difference between a metal and non-metal? Okay, we studied that in chapter 1 as well, right? Metal, why we call them metal? Because they're shiny, right? They're mostly solid, they're malleable, right? And most importantly, metals conduct what? Electricity. And also they're a good heat conductor as well. Is that right? So these are some attributes for metals. And non-metals, the reason they're called non-metals because they don't have a what? A general universal property. Okay, they could be solid, it could be liquid, it could be gas, and also they're normally not shiny and they're brittle and they're not malleable, and also non-metals normally they don't conduct electricity or what? Or they don't conduct heat as well. So these are some difference between metal and non-metals. Okay, so B. To produce the element nickel, the metal nickel, oxygen gas is reacted with the ore of nickel sulfide. Okay, this is the formula of nickel 2 sulfide actually. And this is the reaction. Using oxygen to get nickel out of nickel sulfide. And if you take a look at this reaction, quick question here is, do you think nickel in the ore is oxidized or reduced in the end?
Would it be oxidized since you're losing?
You're thinking the right way, but think about, is this nickel losing or gaining electron?
Gaining, so it'd be reduced.
It's reduced. Gaining. Why gaining? Because take a look, the charge of the nickel here is what? 2, right? Sulfur is 2, so charge is what? 2 plus. And now after you change from nickel sulfide to nickel metal, the charge is 0 because metal is neutral. So that means what? You gained 2 electrons. That's how nickel sulfide can become what? Can become nickel. So this process, nickel is actually reduced, gained the electron from where? From sulfur, actually, not from oxygen, from sulfur. Okay, number 3, write the chemical reaction analogous to cadmium. Okay, cadmium, this is the reaction analogous of that nickel sulfide treating with oxygen to get nickel, and the same treating with oxygen to get cadmium, very similar reaction. And the same way, cadmium in this reaction is also what? Reduced to become the metal cap. Okay, and the last question is very easy. Why the release of sulfur dioxide is a serious problem? Because both reaction with sulfur dioxide. We know sulfur dioxide is one of the bad gases in chapter 1 we described, right? They are irritant. Okay, they pollute our atmosphere, and also more importantly, sulfur dioxide can be further oxidized and eventually becomes acid rain or contribute to acid rain. So these are something, again, like I said, by now you should be able to integrate the information from across different chapters, because again, we're getting ready for the final. Right? So today, okay, we're going to study a very unique type of galvanic cell, okay, called fuel cell. Okay, fuel cell is still within the scope of galvanic cell. What is a galvanic cell? We studied in the first half. What is galvanic cell? It's the basic unit that what? Converts chemical energy into electricity through what? The transfer of electron. Okay, that's galvanic cell. Fuel cell. Okay, fuel cell is a galvanic cell or voltaic cell. That means the principle is the same, but there is a difference. Okay, there's a difference. We know for no matter what type of batteries we've studied in the first half, alkaline battery, nickel cadmium battery, lithium ion battery, the chemicals are where? Where are the chemicals located? Inside the cell, right? They're placed inside the battery already. It's pre-wrapped together, ready for you to what? To use. In the fuel cell is different. Okay, in the fuel cell, that the chemical reagents are not inside the battery. They're actually keep being pumped into the battery so that they can react to produce electricity. But the chemicals, the fuels, are not pre-placed inside the battery yet. They're being pumped into the battery. And also, of course, because it is called a fuel cell, one of the main reagent in fuel cell, galvanic cell, is a fuel. What is a fuel? Okay, we studied in chapter 3 and 4. What is a fuel? Fuel is something where they can what? Can be oxidized, right? Can react with oxygen to what? To burn, to produce heat and energy, right? Same. In the fuel cell, one of the reagent is a fuel. Okay, that's something different between fuel cell and the traditional galvanic cell we studied in the first half. Okay, first, again, the chemicals are not in there yet. They're getting into there continuously. And also number 2, we're using a fuel. And of course, in order to burn a fuel inside the cell, we also need what? We also need oxygen, just like we're burning a fuel outside in a car. Okay, so these are something difference. Unlike conventional batteries, fuel cells operate on an external supply of fuel. Okay, external supply means what? You have to keep pumping fuels into it. That is electrochemically oxidized inside the cell, and then they require an external supply of oxygen or other oxidants. Okay, most commonly used is just oxygen in the air. Okay, they do not run down or need to be recharged. Why? Because again, like I said, the chemicals are not pre-placed in it. They're what? They're keep being pumped into it. So as long as you can keep getting fuels in, they never run down. Okay, they never run down. So let's take a look. One of the most commonly used, or the one actually are used daily. Okay, we don't see that nowadays, but there is a chapter discussion topic. You guys can watch 2 videos. They're actually around us. Okay, now maybe not in South Carolina, I'm not sure, but they're around us in the United States. Okay, one of the most commonly used fuel cell is hydrogen fuel cell. Okay, hydrogen fuel cell means the fuel is what? Hydrogen. Okay, the fuel is hydrogen. So this picture shows you all the reactions of hydrogen fuel cell. Then we go back to next page. We're going to take a look. What is the principle of a hydrogen fuel? How does it work? Okay, first let's take a look at the reaction. In a hydrogen fuel cell, we're using hydrogen gas, which is the fuel. During the process, hydrogen gas is H2, becomes 2 what? Hydrogen plus. This process, hydrogen lose or gain electron. Hydrogen becomes hydrogen plus. Means what? Lose or gain electron?
Lose.
Lose electron. right? Lose 2 electrons. And we call this process oxidation. Okay, this is the oxidation half reaction. Hydrogen lose electrons. And of course, we know whenever lose the electron, we call the electrode what? The anode, right? Next. On the other hand, if we're burning a fuel in a fuel cell, we also need an oxidant. Like I said, the most commonly used oxidant is just oxygen in the air. So we have oxygen in the air that gains those 2 electrons from hydrogen. In the meantime, after gaining electrons, it will combine with those 2 hydrogen plus to generate what? Water. Okay, losing electron, gaining electron. Not only it gains the oxygen, not only gains the electron, but also gain what? Those 2 hydrogen plus altogether become what? Water. And we call this half reaction the reduction half reaction. Of course, that's the cathode reaction. If you add these 2 reactions, half and half reaction together, like I said, everything on the left side add together, everything on the right side of the arrow add together, and you cancel that species out on both sides. What do we cancel? 2 hydrogen, 2 hydrogen, 2 electron, 2 electron. What do we get? We get this. What is this reaction? This reaction is basically what? Hydrogen reaction with oxygen and to give what? To give water. This is the same reaction if you burn hydrogen. If you have a hydrogen balloon, you burn it. This is the same reaction. Hydrogen react with oxygen to give what? To give water. But, like I said, these half reactions happen inside what? A fuel cell. So we're not technically burning it. We're actually creating electron transfer without burning. Even though they're a reaction, we're not burning. That means this reaction, even though it is the same reaction as burning, you don't have any flame, you don't have any little bit heat, and you don't have providing any light, flame, fire, nothing. Typical of a combustion reaction. Does it make sense? That's what happened inside a fuel cell. Okay, by the way, have you guys seen or watched movies about burning hydrogen? Have you guys watched the movie The Martians? Matt Damon? When he was trapped in Mars, he had to grow potato. You know, grow potato, you need water. Well, how he does is he actually has used the fuel from the rocket, the hydrogen. Rocket uses hydrogen and use the hydrogen to burn, and then get water to water the soil to grow potato to survive. If you watch that, if you remember that scene. Okay, the same idea. Again, burning fuel, the reaction is the same as what happened inside the fuel cell, but the difference is inside the fuel cell, the burning of hydrogen has no flame, generates little heat, and a lot more efficient. Okay, so these are the reactions, but let's take a look. Okay, let's take a look. What's really happening inside a cell? What the cell look like? This is a scheme of a hydrogen fuel cell. Okay, like I said, in a hydrogen fuel cell, the hydrogen and oxygen are not inside pre-placed in there. They're keeping being what? Supplied inside the cell. They're keeping pumped in. So when hydrogen pumps in, hydrogen will lose electron to become what? Hydrogen plus an electron. And of course, electron will be transferred through an external circuit to create what? Electricity. That's what a cell works. Now, what happened inside here is, after the electron goes to here, again, this is the anode, that's the cathode, the electron will be taken by what? By the oxygen. Okay, from outside, taken by the oxygen. Of course, the oxygen is being pumped in as well. And meanwhile, the hydrogen plus from the anode will be diffused through a membrane. This membrane can allow hydrogen to be diffused, called the proton exchange membrane. So you can see that these are positive charge are hydrogen plus. After the lose electron goes from an external circuit to create electricity. The hydrogen actually diffuse across the membrane to where? To oxygen. Okay, to oxygen. And oxygen basically takes what? Takes the electron from an external circuit and what? And the hydrogen plus that is diffused from across the membrane to give you what? To give you water. You guys see that? Hydrogen loses the electron to become hydrogen plus. Hydrogen plus diffuse to where? To oxygen. And meanwhile, the electron is transferred from anode to cathode, also go to where? To oxygen. Eventually give what? Give water. Of course, water will be what? Will be exhausted outside the cell. Okay, this is what happens inside a hydrogen fuel cell. Does it make sense? And you can see that through this process, if you keep pumping hydrogen and oxygen, you can keep generating what? Electricity. Okay, electricity. Okay, this chart shows you, again, like I mentioned, what is the difference between burning hydrogen and burning hydrogen inside a fuel cell? What is the difference? Okay, the difference, again, is burning is a very rapid process. It has what? Flame. It generates a lot of heat that you cannot control. But inside a fuel cell, the process is very slow, it's smooth, no flame, quiet, efficient, and what? And generating electricity. The energy is not released as heat. The energy is actually converted to what? To electricity. Even though the reaction is the same, but they're produced in different ways. Does it make sense? Okay, that's the comparison between combustion versus hydrogen fuel cell. Okay, and finally, you guys might wonder, I said hydrogen fuel cell is one of the most commonly used one. Where it is used for? What do you think it is used for? Where do you think we use hydrogen fuel cell? Where do you think that electricity is used for?
Cars.
For cars. Okay, that's why here I want to show you a hydrogen car. Okay, hydrogen car. This is the scheme. Show you a hydrogen car. Okay, of course, the main part is the fuel cell. What the fuel cell does is what? To generate electricity. And electricity, of course, will be used to power a motor, and also electricity can be saved by a battery as well. In order to have fuel cell working, you need to provide the fuel. What is the fuel? Hydrogen. And in order to provide hydrogen, you need to carry what? Hydrogen tank. Okay, just like your gasoline tank, you need to carry the hydrogen. Oxygen you don't need to carry because we have oxygen in the air. So you can always get oxygen in the air, but you do need to carry what? The fuel. What is the fuel? Hydrogen tank. So this is the general scheme. Of course, there's other things, auxiliary battery, power controller, transmission, etc. But the main component is that fuel cell. And the car is powered by what? By the electricity from the fuel cell. And of course, some extra can be stored in the battery for uses as well. Okay, but the main, again, fuel are stored in fuel tank. Okay. This is not future. Okay, not future means this could be our future, but what I mean not future is hydrogen cars are on road. Okay, may not be in South Carolina, but it's not very popular. Actually, it's common in some states, especially California. Okay, it's not like something new concept. People are actually driving that car. Okay.
Toyota's converting one of their internal combustion engines right now to run on hydrogen.
Yes, I mean some company I know they use methane, even natural gas to burn, but hydrogen car is something new. Not all states have it because you have to have the infrastructure. You have to have hydrogen station, right, to charge hydrogen. But hydrogen costs. The cost is the one we're going to talk about right away. Like here, some limitations. Okay, why you don't see hydrogen car everywhere? Because of these limitations, but they are actually around us. This is one of the directions. Okay, you may wonder why we want, because the heat efficiency of hydrogen is very high. Okay, provide a lot of energy. Number two is, what do you think the product is? Hydrogen fuel cell, we just say, what's the product? Water, right? Think about it. Your car only emit water means what? That's really zero emission. Okay, you're not using carbons. You're basically burning hydrogen to what? To just drain water, like your car is just dumping water. Okay, that's something, again, one of the directions. I don't know how it goes. Eventually, we may see that in the near future. Okay, but here are, like I said, some challenges or limitations about the hydrogen fuel cell or hydrogen cars. Okay, and this is the website. You can check more about. They update more. Sometimes it's solved, sometimes not. For example, first is how do you get hydrogen to consumers? Like you have to have infrastructure, so you have to transport hydrogens to the gas stations, right? To hydrogen stations, and also onboard hydrogen storage, like the hydrogen tank on the cars. They have to be safe because hydrogens are explosive. So the hydrogen tank has some safety concerns, and also the cost of the vehicle. Okay, if you're trying to save money by using alternative energies, but it turned out the cars cost a lot more than your internal combustion engine car, then it's gonna be cost issues to consider about. And also, how durable and reliable the fuel cell is still under testing. Okay, and here are something we briefly talk about the challenges, how people are doing that. Okay, nowadays. Okay, how these are challenges, but we're still working on this. So how hydrogens, for example, are produced, how they're stored, some progress so far to briefly show you guys. First is where is hydrogen coming from? Okay, how do we get it? We don't have hydrogens in the air. Okay, so hydrogens are actually produced from hydrogen-containing compounds. Okay, mainly nowadays, the source of hydrogen is still fossil fuels. It means what? You still cannot get away with fossil fuels. You're driving hydrogen cars, but the hydrogen cars, against 95% of the world's supply of hydrogen is actually from methane. What is methane? Natural gas. Okay, this is the reactions showing how do we convert methane to hydrogen. Okay, hydrogen. Both reactions. Okay, this is the first reaction, second reaction. Both reaction, in fact, needs a lot of energy. You can see that both reaction are a lot of energy. Means what? Means you cost a lot of energy to convert a fossil fuel to what? To hydrogen. And on the other word, okay, in another word, it means the cost of hydrogen won't be cheap, won't be economical. Why? Because first they're using another fuel. Number two, you use a lot of energy to create hydrogen from another fuel. Okay, from another fuel. Okay, another solution is to getting hydrogen from liquid fuel, such as methanol. Okay, methanol is a hydrogen-rich fuel. Okay, rich fuel. So the difference between here is because methanol is a what? Is a liquid. Okay, natural gas is a gas. You still can have a gas tank in your car, but methanol is a liquid. So compared to natural gas, methanol is easier to store. So this is the converting. You can see that has a lot of fragments. Basically, we call reform from methanol to hydrogen. Okay, to hydrogen. But again, you can see how many processes we're talking about and how much energy needed, and this won't be an economical process. And number two is somebody proposed, how about we have a onboard reformer, means you put this device in your car. You just basically fuel your car with methanol, and your car will gonna convert methanol into hydrogen, which is one of the solutions. But again, this process will add cost and also maintenance demands to the vehicle. Remember, your cars have to be reliable and have to be doable. Okay, you're adding an extra component onboard reformer, you're gonna cost adding the cost and also create extra process for maintenance. Okay, that's two main sources nowadays for hydrogen. Again, both process means hydrogen won't be cheap. Okay, very costly. Okay, now another direction of getting hydrogen is basically from another hydrogen-containing compound. Basically, one of the most abundant compound on our planet is what? Water, right? Remember, water has what? Water has hydrogen in it. So basically, if you could split water to produce hydrogen, then you basically can solve the problem permanently, because we have a limitless amount of water, okay, technically speaking. But the same, splitting water into hydrogen and oxygen, these two elements, also needs a lot of energy. Okay, this is a lab scale device. You can actually do this at home. If you have this tube, you can actually buy it if you're interested. Okay, this is a lab scale device that can split water into hydrogen and oxygen gas. Okay, basically you convert, you connect these two tubes. These are all water. Okay, this is the water reservoir. These are two tubes to collect hydrogen and oxygen. And then you connect both ends with a battery. Okay, in order for this to work, you at least need a 9-volt battery. Okay, the other batteries the voltage is too low. At least you need a 9-volt battery. Okay, this 9-volt is not big, but at least you need a 9-volt battery. And then after you connect, you will see that both ends will start to bubble. Okay, what is the bubble composed of? One end is hydrogen, another end is what? Is oxygen. Okay, it's oxygen. And you will also notice that the volume of the hydrogen will be twice as much the volume of oxygen. Why? Because water is what? H2O. So when you balance the reaction, you will find out for one molecule of hydrogen, you will get what? One molecule of oxygen, you will get what? 2 molecules of hydrogen. That's why the volume ratio of hydrogen and oxygen is 2:1. Okay, and we call this cell, okay, this small scale cell, electrolytic cell. Okay, electrolytic cell. Okay, why electrolytic? Because now we're not creating electricity. We're doing what? We're using electricity or a battery to what? To split a compound. Okay, that is something different from what we learned before. Before we were using chemical reaction to create electricity. In here, we're doing what? We're using electricity to what? To split water. So what happened in the electrolytic cell is basically we're converting electric energy to what? Back to chemical energy. Does it make sense? Okay, remember chemical energy in where? In fuel, in hydrogen. Hydrogen is a high energy element. So this is a different type of cell called electrolytic cell. Now you can take a look at this chart. Shows you how much energy you need. Okay, remember we said earlier we actually practiced in chapter 4, I think 3 or 4, burning hydrogen. Okay, burning hydrogen to give water basically will release. Okay, the charge is the heat is negative means what? Release 249 kilojoules of energy per mole of hydrogen. Okay, negative again means exothermic release. And then if you want to split water back to hydrogen and oxygen, basically you need what? You need absorb 249 kilojoules energy in order to do that. And of course, from an electrolytic cell, the energy absorbed is from where? From the battery. Okay, so that's why we're saying we're converting the electric energy to what? To chemical energy now stored in what? In hydrogen. Okay. So, like I said, nothing is it's not that easy. You can split water, but this process needs what? Needs the same amount of energy whenever hydrogen burns to release. Okay, that's the reverse process, and that reverse process needs energy absorbed. And energy absorbed coming from where? From the battery. Okay, from the battery. Here is the chart, shows you the experiment. Like I said, you can do this at home. Okay, just 2 wires, 2 test tubes in a beaker. You can see that connect to a 9-volt battery. You will see that the water start to bubble. Okay, again, hydrogen, oxygen. You see that 2:1. Always you collect two volumes of hydrogen per 1 volume of oxygen. Okay, they're always 2:1 ratio. Okay, now I think you guys won't confuse, but I want to add one extra word is electrolysis of water, splitting water with electricity is different from boiling water. Okay, you both see bubbles, but the bubbles contain different things, right? In electrolysis of water, the bubbles are what?
Oxygen.
The oxygen action, they're elements of water, right? The constitution elements of water. But when you boil water, the bubbles are what? What is it? Water vapor, right? It's water molecules. So what happens? When you boil water, you're breaking the hydrogen bond of water. But when you electrolysis, like split water with the electrolytic cell, the water is actually what? Broken. The covalent bond is broken. So different types of forces are broken when you boil or split water. Okay, just keep in mind that's something. Okay, and 2 more about getting hydrogens. Okay, again, people are doing progress. Okay, solving this problem, making progress on how do we get hydrogen. This is one of them. Again, I think it's still research scale. Instead of using battery, okay, this experiment use sunlight. Okay, use sunlight to split water. Okay, of course, in order to split water, you need high energy photon to hit on some composite board or something. You can read more. I don't know about this research, but the basic principle is use sunlight, the energy from sunlight, to split water to create hydrogen and oxygen. Okay, of course, you can see the efficiency. Currently, efficiency is what? 14%. It's very low. But good news is you don't need a battery. You need what? You need free sunlight. Okay, this is one of the direction. Another direction is shown here. Okay, you can read more. Is some biochemists, they use green algae. Okay, this green algae have an enzyme that can split water into hydrogen and oxygen. Of course, in order for the enzyme to work, the algae need to be exposed to sunlight. You still need energy from where? From the sun. That's why you can see the algae bottles, the green algae bottles are actually exposed with what? With those light bulbs. Okay, because they need light energy to what? To split water. But again, it's called biosynthesis, biophotolysis, because we're not using energy from a battery, we're using energy from the light and catalyzed by enzymes from microorganisms. So again, these are all kinds of research directions asking you to think about if you're in the future in the field of something like this. These are some direction to think about, right? So let's how do we get hydrogen? Where hydrogens are coming from? Okay, next challenge is how do we safely store hydrogen, especially in a tank in a car? Okay, here's something to think about storage. You may think, oh, well, it's nothing bad to store hydrogen in a car, just use a tank. But it's not that simple or not that straightforward as you would do for a propane tank, for example, because like I say here, as a gas, hydrogen has a very low density because hydrogen is just made by two small hydrogen atoms. The density of hydrogen is very low. That means the hydrogen gas takes a huge amount of space, okay, because density is low. For example, at sea level and room temperature, hydrogen occupies a volume of 11 liters, almost 4 gallons per gram. You have to think about it. 1 gram hydrogen, the volume is 4 gallons. In comparison, 11 liters of gasoline, 4 gallons of gasoline has a mass of 8.7 kilograms. You can see what the difference is. Okay, what does this tell us? This tells us what? It's very hard to confine hydrogen or store hydrogen in a good amount in a what? In a small space. Is that right? Gasoline, we can store 4 gallons what? In a tank. But hydrogen we cannot because it's a gas. You can see that 1 gram of hydrogen will already have how many gallons? 4 gallons. Okay, this again tells us storage hydrogen is always a very, very big challenge because hydrogen density is so low and it's so hard to compress hydrogen into a small space to be stored on a vehicle. Okay, one way to do that nowadays, okay, this is what picture of a hydrogen tank looks like, okay, is to use metal hydrates such as lithium hydride, because lithium hydride, these metal hydrates can selectively absorb hydrogen on it. So basically they can increase the amount of hydrogen that can be squeezed into a tank. Okay, this is the picture showing what's inside a hydrogen tank. You have a lot of metal hydrates particles, and these particles will absorb hydrogen temporarily on the metal hydrates, and when you need it, when the pressure is lowering, the hydrogen can be released for us to use. Okay, for us to use. So these are some of the challenges, or two of the most important challenges we're talking about if we want to use hydrogen fuel cell. One is how do we get hydrogen, and how do we get hydrogen in an economic way? And number two is how do we store hydrogen on board on a car? Okay, again, this is a picture showing hydrogen tank. Okay, I think some hydrogen tanks are made by carbon fiber because it's very strong materials. Okay, with that being said, I want you guys to watch these two YouTube videos. Okay, they're both reviews of hydrogen cars. Okay, they're live reviews, they're real reviews. Okay, those hydrogen cars are actually, again, like I said, they're on road. Sometimes you may not realize it. Okay, one is by Toyota, another one by Kia, I think, or Hyundai or Kia, I forget. But these two videos are very good, and the reviewer is one of my favorite tech reviewers. If you guys watch like tech, Mr. Mobile, Michael Fisher, he's reviewed this. It's from a couple of years ago, but these two videos are the discussion assignment for chapter 8. Okay, after watch the video and write an essay about what you learn about hydrogen cars, what you think about hydrogen cars. Okay, he had two reviews. You can watch them by the time order. I forgot which one. This may be the first one he drive it. All right, so that's about fuel cell. Okay, that's about fuel cell. The last part of this chapter, okay, we want to talk about another direction of using batteries. Okay, another direction of alternative energy, that is photovoltaic cell. Okay, photovoltaic cell, you can say it is a word combining two parts. Voltaic cell is again what? Create electricity. Okay, a basic unit to create electricity. But photo, this word means what? Means light from photon. So what is a photovoltaic cell? Photovoltaic cell is basically a device that converts sunlight directly into what? Into electricity. We're not talking about chemical reaction. We're talking about convert sunlight directly into electricity. That is, again, another direction. Okay, I think it's more promising direction of using alternative energy, using photovoltaic cells. Okay. The sun hits the earth every hour with energy enough to meet the world's energy demand for an entire year. We're exposed to a lot of sunlight, but so far we're not actually using them in a good amount. Okay, we're actually using sunlight energy in a very minimal amount. Okay, our society has been using photovoltaic cells. It's not like this is a new something new. We're using them, like I said, but we're using them at a very minimum level. Okay, minimum level. And like I said, here currently less than 1% of electric power generated in the U.S. are directly from sunlight, from solar energy. But again, we are using that. Have you guys seen a device like that in a highway or somewhere? The traffic light, they're actually powered by a panel. Okay, this panel is actually made of photovoltaic cells. Okay, so let's take a look this part. Okay, how this part can be promising to us by providing energies. Okay, this is a picture showing you some remote area of on this planet Earth. You see that more than 1/3 of the Earth population, they're actually not connected to electric network. Okay, you guys, we're all privileged to use electricity. We even think about where the electricity come from because we're connected to a huge network of electricity. But a lot of places on this planet Earth, they don't even have network. Okay, they have electricity in that country, but they don't have network, so they have no access to electricity. So photovoltaic cell, by converting sunlight to electricity, will be what? Will be very promising to these places as well. Okay, we'll bring electricity to isolated places like shown here. Okay, again, because you don't see the high wire above them, they don't have electricity access. Okay, so not only photovoltaic cell is an alternative promising direction of energy, but also again will solve the unbalanced energy distribution, especially non-access to electricity for some isolated place on this planet. Okay, this picture, I think they're being updated as well. Okay, it's from the NREL website. Okay, called National National Renewable Energy Laboratory. Okay, this is the website of it's the government website, showing you the solar global horizontal radiation. Basically, how much radiation you're exposed every day from sunlight across the United States. You can see that the parts we're living with, like the east, southeast, and southwest part, we're actually exposed to what? To a very good amount of sunlight. You can see how much energy we're talking about every day. Okay, now the north part is a little less than us, but you can see southeast to southwest, California, this Arizona. The radiation strength is what? It's very strong, and tells us what? Solar energy can be totally applied to what? To this whole country, especially in the south part of this country. Okay, and like I said, the device of using photovoltaic cells are around us. Some of you guys have used it, have seen it, like the traffic light. Another device is something like that. You can actually put it on your backpack when you're hiking, when you're backpacking, and you can use that sunlight. Of course, this is the panel. You can charge your iPad, you can charge your laptop, and this is the picture. I always want to get a set of lamp. This costs like around $1,000. Okay, this is the company I like a lot. Jackery. Okay, it's called Solar Saga. Okay, they provide you the panel, and also they provide you a large, like a powerhouse. So during the day, like you're backpacking, you're hiking, you're camping, you can put the panel on the floor and get in the sunlight and charge the power pack. And this is 100 volts. Means what? Means you can actually use it for light bulb, for power fan, for like a personal heater during the night in a camp. Okay, this is very nice. They're both available on Amazon, but again, it costs a lot. So I think last time I checked, these set cost more than $1,000. Okay, but the price is going down, of course, daily. It depends on how people are getting the solar panels.
Everybody had a bunch of little solar panels like that on this big trip, the big backpacking trip I went on last summer.
Right. You have it?
It's in my car right now. I'll keep it in my car.
Oh, nice. Yeah, like I said, these are something you're actually using it daily. But just, again, the efficiency is not the best. I think 30%, 40%, but again, you're free, right? You just put in there. If the sunlight is good, you can enjoy it. And during the night, you got a full powerhouse there. And this is, again, 100 watt is good enough for even for a personal heater, for a fan. Okay, maybe not for cooking, but in general, daily life during the night, you can actually use it in the light bulb and everything, right? And of course, those are small scale ones. This is a picture of a big one. Okay, this is a solar panel array in a photovoltaic power station. Okay, like a power plant. Okay, this one is in Germany, and the peak capacity, you can see that this power plant can generate 12 megawatts. Okay, or 11.4 megawatt, while a typical nuclear power plant generates 1,000. Okay, you see the comparison. Okay, of course, compared to a nuclear power plant, this one is what? It's just maybe 1% of it. But again, this is totally what? Renewable. It's free. Okay, as long as you have the infrastructure, you're getting power, a lot of power daily, without worrying about building a power plant, without about the fuels, without worrying about what? The waste. Okay, but again, solar power power stations are still in small scale. Okay, most times they may provide electricity to a village, to a city, to a small town, or a lot of times I think here I'm seeing is they might provide electricity for a factory, for a company. Okay, have you guys drive to the east? I think I forgot. Either you drive I-20 east or I-26 west. I'm sorry, I-20 west or I-26 west. You will see a small power station like this. You can actually see it on the highway. I forgot I-26 or I-20, but you will see that. But I think that is actually built for a factory nearby. Okay, but again, you actually see those around us. Okay, but okay, in summary, no matter we're using a small device or a large array, all these panels are constructed in this format. They're built by individual photovoltaic cells. Okay, the cell is still the unit, tiny cell. And of course, the cell will arrange together to get a module. The module will stack or parallel align together to get a panel. Okay, the principle there is the same, no matter small or big. Okay, this is again what a solar panel looks like. Okay, no matter small or big, they're composed of small photovoltaic cells. We call that PV cell. Okay, you will see PV a lot. PV stands for what? Photovoltaic cell. Okay, now the last part of this lecture, we want to briefly talk about how does it work? How these panels, how these cells that can convert solar energy into what? Into electricity. Okay, let me ask you guys. Okay, we have been talking about this topic many times this chapter. In order to create electricity, what do we need? Think about the first part, the battery, traditional battery. In order to create electricity, we need what?
Electron
Transfer of electron, right? We needed electron to what? To move, right? In the first part of the battery, we're using the electron transfer from what? From chemical reaction, from the anode and the cathode. The substance is transfer of electrons. One donate, one accept. Here in photovoltaic cell, this is what happens. This is what happens. In a photovoltaic cell, PV cell, we usually have layers of semiconductors, mostly used silicon. Okay, we have layers. When sunlight hits one layer of silicon, it will dislodge or dislocate electrons from that layer. And because these two layers are separated, then the electrons dislodged can only go through an external circuit to what? To another layer. And that movement of electron creates what? Electricity. Very simple principle is use the property of a semiconductor which will hit by photon, sunlight photon, high energy photon. And the photon will kick electrons out from one layer, then what? Electron can move across to what? To another layer. So this is basically very simple scheme of PV cell. Okay, what PV cell does. And this is the picture shows you the electrons, how electrons are arranged in silicon, and we're going to talk more about it. Okay, this is the picture of a silicon. Silicon has 4 valence electrons. So all silicons are actually covalent and bonded together, sharing 4 electrons with each other. So we have a network of silicon. Each one has 8 valence electrons after the network. It's very similar to diamond, okay, silicon structure. Okay, in silicon structure, because each silicon has 8 valence electrons, so you need high energy photon to kick electrons out from one silicon to make it what? To make it free, because you need an electron to move. Okay, this process is feasible, but in reality, the electron, in order to be freed from silicon, you need very high energy photon, and also it's relatively difficult. Again, the reason is every silicon has what? Has 8 valence electrons. So it's very hard to free an electron. Okay, so in reality, in order to make electron freer, make electron transfer or knocking out the electron from one layer into another easier, in reality, there is a very common technique used in making PV cells called doping. Okay, doping. What doping does is to add atoms with either excess electrons or fewer electrons into the silicon layer. Can we add a tiny amount of atoms containing excess electrons or fewer electrons to the silicon layer? This process will make electrons flow much easier than pure silicon. And the tiny atoms added are called dopants. Okay, the process is called doping. Okay, you may want to understand what does it mean adding atoms with excess electrons or fewer electrons. For example, usually we can add 1 ppm of gallium or 1 ppm of arsenic into pure silicon. Okay, oh no, first 1 ppm means what? 1 parts per million means the concentration is very low. You're not adding a lot, you're adding a tiny amount. Now let's take a look at these two elements. We know silicon, the valence electron is 4. How about the gallium element? What do you think the valence electron? If you guys remember, gallium in which group?
13.
13 group. So how many valence electrons does gallium have?
3.
3. Arsenic in which group? Arsenic in which group?
15.
15. How many valence electrons? 5. So think about it. Silicon has 4 electrons. So arsenic has 5. Means what? Arsenic has 1 extra electron than what? Than silicon. Gallium has what? 1 less electron than silicon. So this is what happens. Okay, this is hard axis. If you add arsenic in one layer, then the arsenic will actually provide a free electron to move. Right? Because arsenic has what? 5. And if you add gallium to another layer, because gallium only has 3, so that means you actually have an empty hole in that one, in the other layer. So what does it tell you? Now you expose this one to sunlight, what happens? That extra electron can easily move to where? From the extra spot to where? To the hole. And this process, again, will make the movement of electron a lot easier than before. And we call this process doping. Okay, now after doping, these two layers, or these two semiconductors, have two very important names in PV field. The one doped with arsenic with extra electron is called the N-type semiconductor. The one doped with gallium with a hole is called the P-type semiconductor. Okay, usually a PV cell like this is called a PV junction. Okay, you will hear that a lot. What is, I'm sorry, PN junction. What is P? P means what? The one doped with less electron, fewer electron. N means the one doped with what? With extra electron. Okay, that's why we have two types of semiconductors. We don't have pure silicon here now. We have doped ones. N-type with abundance of electrons. P-type with what? With empty holes, with deficit of electrons. Okay, so with that, you can see that this is what happens in a PN junction. Two layers of semiconducting materials are now placed together. Again, N-type has what? Extra electrons. P-type have what? Empty holes. Okay, deficit of electrons. So when you have sunlight come in, the electrons now have a direction to flow. Not only easier to flow, has a certain direction from where? From N-type to where? To the P-type. Does it make sense? Okay, not only make possible the conducting of electricity, but also ensure that the current flows in a specific direction through what? Through the cell. Does it make sense, guys? Okay, this is what happens, or very commonly used in PV or in PV cell PV. Okay, very quickly, guys, I want to ask you, some solar cells designed, instead of using gallium or arsenic, they use phosphorus and boron. Which one will make N-type semiconductor? Which one will make P-type semiconductor? Very quick. Instead of using gallium or arsenic, some use phosphorus and boron. So which one will make P-type? Which one will make N-type?
Phosphorus would make the N-type.
Phosphorus will make the N-type. Boron will make the P-type. Do you agree? Phosphorus has how many valence electrons? 5, right? Boron has what? 3. So phosphorus has extra electrons, so we'll make the N-type. Boron will make the P-type. Very good. Okay, next. Only photons with enough energy can knock electrons free from the doped silicon. Okay, as of 2019, silicon-based solar cells have efficiency of only 27.6%, less than 30%. Again, like efficiency is very low. So one way to increase the efficiency is to add multiple layers. Okay, you can see that these are multiple layers of solar cell. That's a single layer solar cell. Okay, these are ones that are currently used nowadays. If you want to increase the efficiency, okay, multi-layer solar cells increase the efficiency to almost 50%. Okay, but in order to make a multi-layers, you have to add the what? Add the cost. Okay, add the cost. These designs feature many layers with thickness on the order of 1/10 of a micrometer. Okay, this is the human hair, 50 micrometer. You can see that the layer is how many? 15 microlayer. That means less than the thickness of a human hair. But the multi-layer can increase the efficiency to almost 50%. Okay, and not also explained, I don't know, you guys have seen a lot of houses in South Carolina, and they build what? Solar panels on the roof, right? And the cost mainly is from the panel. Okay, installation is something and maintenance is something, but the cost mainly is from solar panel. And if you're interested in installing that, you're gonna investigate the market, how much it is the cost and how many years you will make money back, right? You spend $20,000 to install the solar panels, but you're getting free electricity now. And how many years you're gonna make the money back until to balance off, and how many years you're gonna live in that house until you balance off the cost for the installation. Okay, I know some companies actually they rent or lease you the panel, and you basically use their electricity, and extra electricity actually can be transferred back to the power plant. Okay, they can actually buy your power generated by your house. Or sometimes like a Tesla earlier, I mentioned earlier, Tesla is doing something to install battery inside your wall. So when you get solar power generating electricity can be stored inside your own battery. During the day, you're generating electricity. During the night, you can use the electricity from what? From the big battery inside your wall. Okay, again, these are some features. And another one, finally, is adding the cost of solar panel is making solar or PV cell grade silicon layer is a very cumbersome and also very expensive process. Okay, I don't know, I'm not an expert on this, but you can see that how many steps are needed. Eventually, you can get a very laser, like a wafer, ready for solar panel. A thin layer of extremely pure silicon ready for solar panels. That's very cumbersome process, and that adds a lot of cost. Again, even solar panel costs are decreasing year by year, but still this will make the process expensive and costly. Right? So that is all, and I have a link, I think in the note area, showing you the manufacturing of silicon wafer and also the refining of silicon wafer. You can read more if you're interested. Again, this process is very interesting, but it costs a lot of money to make silicon. Right? So that is all for chapter 8. We're done for all 8 chapters.